I wanted to leave you with some parting thoughts. For the past 16 weeks, what we have been doing is we've been trying to figure out how the universe works. That's really what this distills to. We live in amazing times, and we've already heard that so many times that it's almost a meaningless cliche, but it is true. And more to the point, you live in what are going to be even more amazing times long after they have patted yours truly in the face with a shovel. The amount of discovery and information that is flooding in at present is, over the past 100 years, is exponentially greater than what mankind has experienced throughout its existence. It's almost too much. It's like trying to drink from a fire hose, and there's going to be even more coming. With this idea of trying to understand the universe comes this concept. This idea of 4 fundamental forces in this universe. At present, that's what we understand. We understand that there are 4 fundamental forces in this universe, and everything else is just a variation on a theme. We have gravity, the strong nuclear force, which is what holds atoms together, the weak nuclear force, which is associated with radioactivity, and electromagnetism, which includes, among other things, light. How do we describe these in modern times? Well, we use general relativity. We use general relativity to describe gravity, and general relativity does a beautiful job of doing just that. And for the strong force, weak force, and electromagnetism, we have quantum theory. Quantum theory describes what happens at a subatomic level. Protons, neutrons, electrons, even smaller particles, quarks, neutrinos, gluons, leptons. It's quite a zoo of particles. Quantum theory is what makes the touch screen on your smartphone do what it do. It is arguably the most successful general theory to date, just in terms of its applications and in terms of its ability to predict and have successful outcomes from those predictions. It's amazing. It really is. So we ought to have this all pretty much wrapped up. Well, yeah, but we have a problem. There's an elephant in the room. There's a conflict. The conflict comes from the existence of black holes. Well, why would black holes create a conflict? Well, black holes, we know, have enormous gravity, so that would certainly be within the realm of general relativity, and we use general relativity to describe some of the things associated with a black hole. That is true. But let's remember, what is in the center of a black hole? A singularity. Now, if anything, a singularity is subatomic in scale. So maybe we could use quantum theory to describe a black hole. Well, just to put this in broad street fighting language, the issue is when we try to put these two ideas together, these two theories together, we get garbage. They don't play nice with each other. Something is missing. There's a missing link between the two. What might that missing link be? Now remember, we've talked about how theories work, how scientific theories work. Gaps in a theory are not a flaw. Gaps are signposts telling scientists, hey, this is where you need to be looking. Well, when we roll the camera backwards to the time of the Big Bang, as we get closer and closer and closer to the moment of the Big Bang, we have discovered some amazing things. Now, here's our Big Bang timeline. This starts at time 0, the moment of the Big Bang, up to 10 to the negative 43 seconds. That is a decimal point, 42 zeros, and then a 1. That's an eeny-weeny tiny piece of time right there. Why is that significant? Well, as I said, if we roll the tape backwards, what we discover is that as we get closer to the Big Bang, and we're talking about fractions of a second, we see that the weak force combines with electromagnetism to form something called the electroweak force. And go back a little bit further, and the strong force combines with the electroweak force to form what's called a superforce. And we anticipate that even further back in time, gravity merges with this force. But we don't know how. This is the undiscovered country. How does that work? If we can understand that, then perhaps we can understand this. That may be the missing link. This is one of the reasons why we have the Large Hadron Collider at CERN, which is literally on the border between France and Switzerland. It's a 17-mile circumference donut in which they accelerate subatomic particles to just this side of the speed of light, smash them together, boy, that's a lot of kinetic energy, and examine the debris that ensues. And with that kind of kinetic energy also comes a tremendous amount of heat, obviously. And one of the ideas is to duplicate the conditions in this time frame. If we can understand what these conditions are, maybe we could gain some insight about how gravity unifies with the other forces. Well, how do we do that? One of the candidates that may have an answer to this is something called string theory. String theory has this for a proposition. It proposes that all matter is composed of strings of energy. And that these strings are exponentially smaller than the particles that we study in quantum theory. Now, this is not as far-fetched an idea as it may seem at first blush, because here's our old friend here. We've already talked about this. We see that there is an equivalence between energy and mass, that they do convert back and forth. And this too has been experimentally proven. So it's not as far-fetched as it may seem at first blush. This came from a mathematical model that was developed in the 70s. It called for the existence of 10 dimensions. A 10-dimensional universe. The 3 spatial dimensions that we're familiar with, plus time, plus another 6 that we cannot readily detect. And as this mathematical model developed, it seemed promising at first, but then anomalies developed, in which you would get, just to put it in rough, crude terms, where you'd get something like 2 plus 2 equals both 0 and infinity. I mean, that type of garbage answer. And it looked at first that string theory was on its way to the trash heap. But then something amazing happened. A theoretical physicist added one more dimension to this model, creating an 11-dimension universe. And the anomalies were resolved. What is the weakness of this idea, this thing called string theory? Well, the weakness is there is no way to directly test it. And I hasten to add, at present. And the reason I do that is because we've been down this road before. Again, going back to the 70s, a physicist by the name of Peter Higgs proposed that quantum theory, quantum physics, quantum theory predicted the existence of a subatomic particle called a boson, later to be known as the Higgs boson. And the mathematics were compelling, so much so that other research physicists got on the bandwagon and said, okay, we're going to find this critter. And they used all sorts of different particle colliders, the Fermi labs here in the United States, but they could not find this particle, no matter what they did. And physicists, scientists, can be pretty salty in their language, as you've no doubt noticed. And as a shorthand, as these scientists were talking with one another, one would say to the other, well, what are you working on? Oh, I'm working on the goddamn particle. And they would immediately know that they're working on the search for this Higgs boson. Well, eventually, one of these physicists decided to write a book for the popular press. And one of the publishing outfits picked up on it and said, yeah, we'll publish this book. And the guy hadn't really thought about a title. And so the publisher said, well, what do you want to call, what do you want for a title on this book? And the physicist said, oh, well, we'll call it The Goddamn Particle. And the publisher said, no, that's never going to fly, and we can't have that on supermarket checkouts. That's not going to work. And the physicist said, well, yeah, okay, I can see that. So they said, how about we call it The God Particle? Well, okay, we'll call the title of the book The God Particle. Well, they published it. It became a bestseller, and unfortunately, a lot of folks misinterpreted the title as some type of theologic pursuit by scientists to prove or disprove the existence of God. I mean, it got twisted all around, and it had really nothing to do with that. But the point of it is, this was an ongoing pursuit for decades. Well, we created this Large Hadron Collider in Europe, on the border of Switzerland and France. This is the largest particle collider in the world, and finally, by using that particle collider, we finally were able to discover the Higgs boson. And it's been verified, yeah, that critter does in fact exist. We caught him. But it's only been within this century, and with the advent of more sophisticated technology, that we got there. Okay, so this is nothing new. We've done this before. We've been down this road before. So the hope is that this Large Hadron Collider may in fact be able to ultimately put this thing called string theory to the test. The strength of string theory. It's mathematical elegance. And remember, when we talk about elegance in mathematical or scientific terms, what we mean by elegance is that we mean that it is comprehensive and it is simple. And all things being equal, this is an elegant mathematical proposition. Furthermore, you should know that seldom, if ever, do we make a discovery in mathematics that does not in some way or another describe reality itself. This is a mathematical relationship that was not created, it was discovered. All mathematical relationships are discoveries, not inventions. The math exists whether we are aware of it or not. And most importantly is this, as I just stated, seldom if ever do we discover something in mathematics that does not in some fashion or another describe reality itself. And we talked about this a month or so back. Here's this guy here. Remember that? The quadratic equation? The quadratic equation, for instance, is applied to this old guy. Okay. This is a quadratic equation. And remember, the quadratic equation is a mathematical reality that exists in this universe, and it describes any number of things, including how a free-falling object will behave. Okay? So that's why I wanted to emphasize this when we talked about it, is how mathematical discoveries almost always describe reality in some fashion or another. So this idea of string theory, it begins as a mathematical discovery. Remember that. So this is what's coming down the road. Keep your eyes out. You'll see this stuff in newspapers, and I don't mean the nerdly press. You'll see this in the Portland Press Herald or the Boston Globe, or even, dare I say it, the Lewiston Sun Journal. This is the stuff that appears in newspapers. And hopefully, after having been here for 16 weeks, doing what we've been doing, you have a better appreciation for how this stuff actually works. And you'll be able to read that and say, oh yeah, I get that. So what I will do is I will leave you with that, and hopefully you will remain curious. There are all sorts of ways out there that you can satisfy your curiosity now. And now, if we've been successful, you now have the tools to go out there and understand this stuff that's coming your way perhaps a little bit better than the average bear. Good luck.